We continue with Anja, exploiting the synergy between optical two-way and microwave one-way ranging in a GNSS constellation based on a simulation study.
Okay. Good afternoon. So I want to talk today about how we can use the synergy between two ranging methods. Two-way optical ranging, just like we have here in SLR, but I always couple it with ranging and time transfer. And then the second would be what we have on the GNSS satellites, so one-way ranging technique. And I always talk about the collocation on ground and in space. Yeah, so because the motivation is from GGOS, so we want to have this collocation on ground of different techniques, for instance here in red cell, even it's an old picture. But we also want to have the collocation in space. Genesis is one of these missions which was proposed, but also we think about others, so in GNSS itself, for instance, that we get more measurement techniques collocated in space. So, the question is then, how do we combine these measurements, and how would an optimal ground and satellite network look like in different measurement techniques? First of all, I want to point out, because whenever I talk about instrumentation which measures at 1 millimeter precision, and even in the range, also in the accuracy, then I said, okay, you always get in simulations then orbits which also fit into the millimeter. And we know that this is not true, because it's not only the instrumentation which is necessary for orbit determination, but also the geometry of the measurements. So what I include into the measurements is ESL measurements, which we'll get on the Galileo satellites, but also on other GNSS constellations. Even though I will talk more about optical intersatellites than on microwave. I also want to enhance the constellation with GEO and IXO satellites. Beidou is an example of that. Not so much for the geometry, but also just to show you how good we can do an orbit determination on the GEO and IXO satellites if they integrate in ESL measurements. Yeah, and last but not least, you cannot get to the millimeter orbit if you do not the modeling right. So you should model the atmosphere where it's the atmosphere is responsible for some delays in your measurements, and also find some better ways of modeling the satellites. Just short, this is what you probably know, to compare different ranging methods. No, this is not. The microwave, you have no weather limitations, what we have in the optical, but you have, at least on ground, no bias control, and you have to model the wet delay and the dry delay, which is different on the optical, where you only have to model the dry delay. Also ionosphere, but this is mostly we can get rid of if we use two wavelengths. One-way measurements, they are very nice for enhancing the geometry. So if multi-users for in GNSS on ground at the same time, but you have two clocks involved, you have to synchronize the clocks, and two-way measurements are very nice, mostly due to the accuracy, because I can do the ground calibration as we do in SLR. And for time transfer, that's then additional one-way measurements. Then there we have to think about the synchronization. So when I talk about intersatellite links, I want to have optical intersatellite links with 1 millimeter precision at 30 seconds integration time. Due to the effect that in the optical, in the intersatellite links, I have no weather, so this is a good idea to do it in the optical. We use an any-to-any scenario, so any satellite will be any pair will be measured. To the ground, I will this collocation and time and ranging from a microwave one-way and an optical two-way ranging technique, also so millimeter and 30 seconds integration time. When you do this collocation, one topic would be the common troposphere parameter estimation, and this is not in my talk, but in a special case of the next talk from Peter will be about a common estimation of tropospheric parameters. One topic I want to address is the weighting. In my simulations, this is easy to find the best weighting of these techniques, but this is probably not the case with real data. So the system looks like this. We have the Galileo system I took for the MEO. I have the additional GEOs, which we see here. It's geostationary satellites or these inclined satellites. Here you see the ground tracks of these different. And my ground network is the Galileo ground station network. So also here you see the intersatellite links which I discussed and the collocated microwave and optical ranging to ground. Just a little bit about the errors. We take into account noise errors. So for the L-band, this 1.5 millimeter in phase, and in the optical ranging to ground, this is optical two-way ranging, this is to the ground. We have a white noise and an additional flicker noise, so we end up very comparable between L-band and the optical. And for the intersatellite links, the same as well. So this is a little bit distance dependent, so also some distance dependencies there. Systematic effects are coming from the troposphere modeling and L-band to the difference between the GMF mapping function and the Venn mapping function, and in the optical we take as Mendes-Pavlis as the real troposphere and Marini-Murray as an analysis, as an error in the troposphere. For multipath effects, we selected some special PCV patterns which look a little bit like multipaths and put this on the L-band. Additional, and then we have biases, constant part of the bias and the variable part of the bias. And we estimate only a constant bias, and very important is how we model then the orbit, and what we estimate is the solar radiation parameters, but you will see this in the next slide. So first of all, we in the real orbit, we take the solar radiation pressure parameters on the box wing model. That's for the real orbit, and the wrong orbit, we use wrong solar optical parameters of the surfaces of 10%, distributed a little different on all the satellites. You see the errors we do in the frequencies, so once per revolution and higher per revolution, and and these errors we put in, we want to get out with an ECOM model, 3 different equations, ECOM2, ECOM2 with additional 3 times per revolution in the B, and then not only 3, but also 5 components in the B direction. For the geosatellite, this is a little bit different. We have a different coordinate system, but and according to this high numbers of estimates here, we also see that here the distribution is very, we can see in every frequency some distributions, and there we thought, okay, we found out that in the 1, it's per revolution, we only have to take the cosine, 2 only sine, 3 only cosine, and in the 4th only sine. This is that we can compare a little bit the number of parameters as we estimate. So the important thing is in simulation is that you have to understand is 3 different steps. And the first step is how big is the modeling error we put into the system. So you analyze the modeling errors, and you see with this equation only estimating ECOM2. In the MEO satellites, we can best estimate about 3 millimeters, and it's getting better if we estimate more parameters. The influence on the IXO is a little bit less because it's a more massive satellite, but also the estimation of more parameters is a little bit difficult also on the geosatellite. So this best possible orbit is unfit on the orbit on really the position of the satellite in space. The next step, what you can analyze in a simulation is then what does the geometry have an effect, and the white noise, because these both go into the formal errors we discussed. And so in the end, you have the modeling errors, the formal errors, which have this geometry, and the white noise inside, and the end, you get all together with the systematic effects. This is then in the end. And we see, okay, the formal errors here, for instance, for the IXO satellites, change if we only have an L-band solution, an L-band and an optical link from ground. Here, from the geometry, we have nearly the same geometry, but different systematic effects. Yeah, this is not here, so nearly same geometry, but different white noise. Contribution is also more measurements. And here, L-band and OISL, we get very nice distribution. Even the ground distribution of all these IXOs is totally different. And if we combine all 3 measurements, we can have from the formal error side very homogeneous and lower than 1 millimeter. Yeah, and in the end, then you have to all these contributions, though the geometry, the modeling, and your systematic effects, and you end here with the MEO with very low ground station distributions in about 20 centimeters level, and you see that it's not possible to estimate more parameters than this for the MEO satellite. If you do additional the optical ranging, you see, okay, I can now estimate more parameters, and I can have half of the error contribution with OISL inside, and also to the IXO satellites. You see that the geometry is better, so you even can get down here, and yeah, having all systems, we really can estimate the best up to all these 3 parameters in equation 3. And even the same contribution here in a radial crossing long track for the different IXO satellites. So even in the IXO satellites, we can get yeah, close to the best possible in this simulation.
Anja, you're
Yeah.
over time.
Yeah, okay. You also can look at the clock and you see that the input clock is the black, and yeah, with L-band you will not reach this in 1 week directly, so you only see the apparent clock, but also here with the others you come much closer to time. Yeah, with daily analysis here, you see also the jumps. Yeah, and the most thing I want to discuss is the weighting. So we have the chance to really find the right weighting, as we can compare the orbit solution with a different weighting. And you see sometimes we are close to what the noise level would say we should give the weighting, but sometimes we are far away. And even if you estimate more parameters, you also see that the weighting has not a very steep minimum, which is the problem in these combination effects. Yeah, and yeah, this I will close. And yeah, this is where we want to go. And thank you very much for your attention.